So Steve has very kindly agreed to be our chair today. He's worked at Ricardo for 32 years in various technical and managerial roles, culminating in business strategy director for the technology business consultancy business before setting up his own consultancy. He is an industrial advisor at the University of Nottingham and a member of the Industrial Advisory Board School of Engineering at Cardiff. He's also a chair of the Powertrain Systems and Fuels Group at the IMechE. So over to you, Steve.
Well, thank you very much, Gloria, for a very kind introduction. So yes, welcome everybody. I hope we're going to have a fun-packed morning. Got a very interesting line of presentations available to us. Because we're using Teams today, note that the chat function, and there isn't a separate Q&A and chat function, so do use the chat for Q&A, but in order to make it a bit easier to filter out the questions, please could I ask that you preface everything with a question for and then who the question is for regarding the presenter, or question for panel, just to make it easier for the team to filter out the questions so they can make it through to me and I can then ask the panel. That will be a big help to everybody. So thank you very much. So let's crack straight on with our first presentation. And that's going to come from David Richardson. David joined Coryton from its outset in 2010, having worked within the specialist fuels sector since 2002. David is the Business Development Director and represents Coryton both at a technical and strategic level, and has had a number of advisory roles at the EU's JRC and also UK government. And David's going to talk to us this morning about the alcohol to gasoline technology and processes. So over to you, David. Thank you.
Thank you very much for that, Steve. Good morning to everyone. Gloria, if you could just go on to the next slide. So just to give you a very quick overview of who Coryton is, we're a specialist blending facility based down in Essex. We're blending a number of different types of fuels, sort of reference fuels, bespoke fuels, sustainable fuels. As Steve said, we've been operational now for about 10 years, and we work and are fully integrated within the automotive, aviation and marine sectors. So we're providing a number of unique specialist fuels for research and development testing. Next slide, please. As I said, we work in a number of sectors. We both do a lot of research work. We're in heavy duty, typically sort of diesel sectors. A lot of work with light duty. Marine is becoming a lot more prominent, especially with the advent of IMO 2020. Also very active within the motorsport industry, which we see as being quite a driver for sustainable fuels. Likewise with aviation as well, looking at SAFs. Next slide, please. So why we're here today? So we're looking at understanding how the industry can cope with the move away from fossil fuels into a more sustainable future. There are a number of pathways to sustainable fuels that Coryton has been looking at, and indeed a lot of the rest of the industry has been looking at as well. These sort of these transition from your typical sort of biofuels that are very common in road fuels today, such as FAMEs, or rapeseed and soya and diesel, and alcohols such as ethanol. There are methanol fuels available in certain markets as well. But what we're looking to do is push the boundaries of what we can achieve within the market, because alcohol-based fuels, FAME-based fuels are not considered to be drop-in fuels. And they also give us little scope for improving or utilising other feedstocks to help complement the liquid fuels that are in the market and to decarbonise them. With that, we've been looking at a number of different technologies, and specifically we've been looking at ethanol to gasoline technologies and methanol to gasoline technologies. And the screen that you can see now gives you a bit of an indication of where they sit within the mix of different fuel types that are available. As I said, if we go back to typical FAMEs and ethanols, these are sitting down in the typical biofuel stream. As we sort of move further up the scale there, we go into a more sort of advanced biofuel route all the way through to e-fuels. And out of those, what we're looking to achieve is to actually change the structure of the feedstocks to one that is more common and one that can be considered to be a true drop-in fuel. Can we go to the next slide, please? So as I said, there's a number of technologies that we've been looking at. We can break these down over sort of the gasoline and diesel ranges. I'm obviously going to concentrate on gasoline. But we've got biogasoline from the ethanol to gasoline process. We've seen this as being particularly viable at the moment. There is a particularly large capability within the market of supply, and it's also relatively energy, or rather the process involved in that is particularly, it doesn't form a lot of energy. It doesn't require a lot of energy to run it, and I'll go on to that in a moment. We've also got biogasoline from the methanol to gasoline process. And you will have heard this within the industry for a number of years, a technology that was designed by ExxonMobil. Again, it has a very similar sort of technology to ethanol to gasoline in terms of its process, although the technicalities behind that are very much different, and they do produce very different types of fuels. Obviously, going through, we've got biogasolines or biojets. These can be sort of produced from sort of pyrolysis fuels. Again, these are only in an R&D stage, and obviously we've got the power to chemicals. Now there's a bit of a mix here with the biogasoline on the MTG route, because these are the MTG fuels are normally considered to be a true definition of what an e-fuel is, i.e. it's a fuel that is produced using carbon dioxide, hydrogen and renewable electricity to power the first part of the process there. Can we just go on to the next slide, please? There is obviously diesels as well, typical HVOs that are in large-scale production at the moment. There are other advanced biodiesels that we've been working on, and you've got these sort of circular economy fuels as well, which is utilising wastes such as maybe municipal wastes from plastics, from rubbers. These are a lot more sort of energy intensive, and there is also a discussion around how they sit within the matrix of looking at their sustainable sort of credentials. So if we can just go on to the next slide, please. Just give you some of the examples of some gasoline products that we've been looking at recently for a number of different applications. We've sort of been concentrating on sort of typical retail type fuels, but also motorsport fuels as well, and looking to help bring the market, or bring those into a market where they can be tested and I suppose effectively sort of signed off. The idea being is that we really want to sort of have a look at understanding, are they really a true drop-in fuel, or are they something that's more aligned to a biofuel that we've seen in the past. So we just go on to the next slide, please. So just to talk to you around the ethanol to gasoline process specifically that we're looking into. The main process here that we want to get to is obviously we're looking to convert biomass into ethanol. And in this particular scenario, looking at ETG, we're wanting to utilise second generation ethanol. And these can be utilising feedstocks such as forestry waste, agricultural residues or straws. And these will go through a very typical hydrolysis and fermentation process using the various sort of catalysts and enzymes, as you would normally to produce any other alcohol. If you can just go on to the next slide. When the ethanol is eventually produced, it's then going into these proprietary technologies, the actual ethanol to gasoline conversion technologies. Now, ethanol to gasoline technology, the good thing about this process is that it produces an exothermic reaction. And this in itself helps to power the process, or the entire sort of process through. And what you're looking to do is split off sort of the water and hydrogen molecules, and you're producing a syngas that's being put back in, that's being reformed again. And then it's going through to a final distillation process. Now, at this point, the liquid that you're producing has a boiling range of somewhere between 300 and 400 degrees C. So at this point, it has to go through a typical distillation process, where you can look to get off your lighter hydrocarbons, which are more typically in your gasoline range. And then what you're also left with is a number of sort of heavier hydrocarbons, typically aromatics, in the sort of C9, C10 plus ranges, that can be utilised in other industries. So much like what we see within the fossil industry, is that there is a use, or rather there are offcuts of the refining processes that you need to think of and find sort of homes for these products. And that's a good thing, because it means that we can utilise these offcuts or these other fractions in other industries, whether it's maybe carrier fluids, where additives are used. Maybe it's within completely different sectors, such as the paints industries, or whether it's something that we can then utilise to adjust the characteristics of the base biogasoline. Also, out of these conversion processes, obviously there's gases that come off that. In this particular case, we're getting bio-LPG, which again, as a vapor adjustment component, again, it's got very good greenhouse gas savings, and therefore could be put back into the biogasolines to help adjust for seasonal variances. Go on to the next slide, please. So ethanol to gasoline is not the only process that we've looked at and worked with various industries. You've also got biomethanol to gasoline, and again, the biomethanol, or rather the methanol stage of this, is where you're really sort of terming the e-fuel stage, because you're taking CO2 out of the atmosphere, and you're combining it with hydrogen to form a biomethanol. Now, again, much like the ethanol to gasoline process, this again is going back into a process that's using a zeolite catalyst. But the technologies and the heats that are used, the process that are sitting behind this, produce a very different type of product for us. It's actually a much lighter gasoline, boiling in the sort of 250 to 300 degrees C range. But likewise, then going through into a distillation column, where we can then cut off the various different types of products. And we found that actually through this process, we're actually getting cuts that are a lot lighter, a lot less aromatics in there, which is giving us sort of fuels that are potentially much more usable in the future. Now, the problem with these processes, or particularly the methanol to gasoline process, is that it's quite an energy intensive process right at the beginning stage. Although the latter stage, much like the ethanol to gasoline process, is exothermic and therefore is producing a lot of its own energy to power the process, beginning stage to produce the biomethanol does take or does require energy, external energy, as I'd say, and ideally that should be a renewable source. Now, there are facilities around the globe that are taking CO2 or carbon capture, whether it's from atmosphere or whether it's from industry, direct feed from industry, and powering these processes through hydro or through wind or solar to produce this biomethanol. And at that stage, we can consider them to be a true e-fuel with very good greenhouse gas savings. We should go on to the next slide, please. So Coryton has produced a number of fuels because we've wanted to look at these fuels in real world applications as well as on the test benches. And we've also done our own sort of fleet studies utilising our own staff vehicles. And as you can see from the slide there, we've looked at sort of trying to concentrate on EN228 or typically EN228 type fuels to understand what does that mean, what does it give us in terms of its greenhouse gas savings, because that's ultimately what we're trying to achieve here. And as you can see, with these types of fuels, you can achieve up to and beyond 80% greenhouse gas savings based on the RED II directive. And this is utilising a mix of the biogasolines, but also the straight alcohol contents as well. And that can increase as you move from an E5 all the way up to an E10, which is quite pertinent, bearing in mind EN228, certainly in the UK, is going to move to an E10 from September onwards. Next slide, please. So what are the advantages and disadvantages of these types of fuels? Well, firstly, it's a true drop-in fuel. Looking at the characteristics of these fuels, and one thing that we wanted to move or sort of educate the industry on from these technologies is that they are not alcohols in their own right. They're not alcohols as you're used to seeing them. The chemical composition has been broken down. It's been reformed to look and behave in the same manner that a traditional fossil fuel looks. So therefore, we do consider these to be sort of true drop-in fuels. Likewise, because of that, and because of the feedstocks that you're utilising, the greenhouse gas savings are tremendous with these. We've been looking at saying, well, how can we get to these net zero figures, or how can the heavy duty industry sort of improve on their industry, sort of improves CO2 output by 30%, for instance, with diesels. They can have a saving of 95%. It's possible that you can achieve more than that with efficiencies in process, methane capture as part of that as well. Also, likewise, the advantage of EN228 now moving up to an E10, we can look to swap out traditional first generation ethanol in place of second generation ethanol, increase up to an E10, and then further enhance those greenhouse gas savings. More importantly, it's backwards compatible. We can address the legacy car park that is in existence now. There's 300 million light duty vehicles in Europe that can all benefit from these types of fuels now. Now, obviously, there are always going to be some disadvantages with these types of fuels, and sort of go through a couple of those types. One, well, who's going to be incentivized to make all of this happen? Ultimately, we're going to be looking at governments to incentivize this. They're going to need some form of crediting systems, perhaps, to look at the other solutions that are involved in this. I mean, again, this isn't a silver bullet solution like you might hear with EV, for instance. It should be used in tandem with that. Likewise, well, what's the availability of these fuels like? Okay, there's 300 million light duty vehicles in Europe at the moment. There isn't enough fuel to fuel all those vehicles at the moment. Hence why we're looking at captive fleet applications at the moment, and why specifically people like within the motorsport industry can really achieve some really big gains by looking at these types of fuels now to help sort of drive that picture and that vision going forward to get to market acceptance, because that's going to be one of the biggest problems here is the cost of these. They are going to be more expensive than fossil, because we've had 120 years of being able to build on that infrastructure, and because of that, the costs are cheap, and those costs will need to start to come up to accept that liquid fuels, in order to be sustainable, you're going to have to start spending more money on them, or to have them severely subsidised. There are some other disadvantages, and I'm going to sort of be very loose with this one and say maybe it's not a disadvantage, but long-term effects of these fuels. So we have carried out a number of tests and studies on these fuels, and from what we've seen so far, we don't see any long-term effects. However, they've only been in the market for a relatively short period of time, certainly when you look at the fossil market. So we're still looking for companies to look to adopt some of these technologies to run their own fleets, their own studies on them, to gain some more data from them. But overall, we do view that with these types of fuels, with these technologies, and that there's a lot more of these coming through in the industry now, and a lot more investment is required, that they will become a real, true sort of viable prospect for us There are markets that we can capture
One
right
minute,
now.
David.
Thanks, Sarah. There are markets that we can capture right now, and we should absolutely be targeting them with all guns blazing on them. But they should always be done in conjunction with other technologies that are sitting outside of these liquid fuel sort of processes. Next slide. I think that might be the last one, actually, Gloria. Yeah. So thank you very much. Appreciate. This is the type of topic you can probably talk around for many hours, and we do with a lot of our clients, actually. But again, if there's any questions around this, we'd really like to hear them. There's a lot of nuances around what we can do, what is happening in the market, and where we believe industry and policy should be pushing towards.
Okay, thank you, David.
Thank you.
That was an excellent sort of overview of everything of the sort of bios and synthetic routes to gasoline, just to get us going. And now I'm going to ask Sam Cockerill to talk to us about the opportunities for bioethanol use in heavy duty vehicles. Sam is the CEO of Libertine FPE Limited, a UK startup making smart engine power generator products for distributed power and transport applications. Sam has over 20 years experience in automotive engineering, consumer product development and strategy consulting. So over to you, Sam.
Thank you, Steve. So yes, I'm Sam Cockerill. I'm going to talk about the prospects for bioethanol use, not as a drop-in fuel, but as a future fuel in its own right in heavy-duty vehicles. I'm going to talk here primarily with my Libertine hat on. I've previously worked for Ensus, which is the UK's largest bioethanol producer, and I'm also a director in Providence Holdings, which has a captive fleet of over 15 heavy-duty vehicles, which moves 150,000 tonnes of potatoes around the UK each year. And that gives me a perspective on what this opportunity might look like and the role that Libertine's technology might play. Next slide, please. So firstly, yeah, I'm a self-confessed ethanol bug, and there are a lot of things going for bioethanol. Firstly, and most importantly, it is a renewable fuel and it's compatible with net zero. And what I mean by that is every unit of energy that goes into the production of bioethanol can be decarbonised, from the fuel that goes into the tractors and the supply chain through to the fuel that's used in production. So just as the grid can be decarbonised in future, bioethanol can be fully decarbonised. Even today, it's a significant step up from the carbon content of fossil fuels. It's also, from a chemical perspective, it's quite interesting because it's a tiny knock-resistant molecule, which makes it really high efficiency and clean burning, and can be used in a variety of combustion modes, so spark ignition, compression ignition, HCCI. It has potential for Euro 7 compliance without aftertreatment, and because of the similarity with other alcohol fuels like methanol, it can be used in blends, which makes it really flexible. As you can see here, it's also got some fairly useful energy density compared to hydrogen, nearly 5 times the energy density of hydrogen at 700 bar, and it's really easy to handle. You can slosh it around as you would with any household liquid, and it's certainly safer to handle than high pressure gases. Next slide, Gloria. It's also worth noting that today, over 100 billion litres of bioethanol produced globally, most of that by the US and Brazil, and other countries as well, are ramping up their production. And despite this, over the last decade, there's really no apparent link between bioethanol production growth and food prices. So for all of those reasons, this is a really interesting future renewable fuel. Next slide, please. Now, the problem in heavy-duty vehicles is this. We're looking ahead to 2050. We're trying to decarbonize all sectors. That includes the heavy-duty vehicle fleet. So 2050, all the trucks that are rolling around are going to be net zero, running around on electrical power and renewable fuels only. But that poses a problem because trucks stick around in the fleet for well over a decade. And so if we're going to get to a net zero fleet in 2050, most vehicles that are sold in 2040 must be fossil free. So we've got to start introducing these fossil free capable trucks by 2030. The trouble is the incentives and the practicality is just not there. And the statement from the joint statement that was made in December last year by these leading European truck companies tells a story which I'm very familiar with my Providence Holdings hat on. Those who operate trucks will not invest in zero emission technologies if there's no straightforward and affordable way to run, refuel and recharge them. When we look at the offerings today for our fleet, where we could substitute in battery electric tractor units, the impact on payload, productivity and upfront cost means that there is just no way we can put those vehicles into our fleet and expect to continue as a transport operator. Next slide, please. So here's a solution, arguably a fairly self-serving solution, but this is what Libertine's proposition could enable. Our technology, which is a platform technology for opposed free piston engines, will enable the creation of a modular high efficiency range extender that can be optimized for 100% renewable alcohol fuels, compatible with existing fuels, and can be used on board series hybrid heavy duty vehicles, so that for those legs and journeys where recharging is not convenient, the truck can continue to operate productively. And by marrying together the best of what's available in terms of battery technology and recharging with renewable alcohol fuels for those other times, we think, get to a commercially viable product during the course of this decade. And this solution is going to reduce the costs and accelerate the delivery of net zero in heavy duty commercial and off-highway vehicles. Next slide. There might be an animation here. Let's see if this works. There we go. Apologies if it's a bit jumpy. So this just shows an animation through a development engine which has been running on the test bench with MAHLE Powertrain in December, and we're doing some further work with MAHLE this year. You can see in the central combustion chamber here, this is an opposed piston engine. There are plenty of opposed piston engines out there. The difference in this case is we don't have crankshafts. We have these two software controlled linear electrical machines on either side, and that means the combustion event can be controlled, the compression ratio can be controlled and varied in every stroke to make better use of renewable fuels like bioethanol, which would otherwise have challenges when it comes to, for example, cold start. Next slide, please. So the work we did with MAHLE last year showed a sort of proof of concept with this running on hydrous ethanol in the test cell. So this was running on 90% ethanol, 10% water. We chose that blend, incidentally, because from a bioethanol producer's perspective, getting rid of the last 10% of water is energetically and operationally quite expensive. And as far as the engine is concerned, it's just not necessary. Unless you're going to blend it away with gasoline, there is no harm at all in the last 10% of water being left in. So we put this onto the test bench with MAHLE. We demonstrated that we can motor and we can combust with a constant compression ratio just with software control, no need for crankshafts. And then we showed that by sliding up the compression ratio, we could achieve cold start performance much better than we could if we had a constant compression ratio. So in this proof of concept work, we've essentially shown that engines using this platform are feasible. And looking ahead, we're looking with interest at how this could be applied on board heavy duty vehicles. Next slide, please. Now, we've just announced some further funding in 2021, which is going to take the test bench engine on the left and turn it into a multi-cylinder engine, not dissimilar to the one you can see on the right. This new package is going to show much higher efficiency electrical machines running on gas bearings with some proprietary combustion systems that MAHLE Powertrain are bringing on board. We'll have better cooling, better packaging, and we'll probably be running for up to an hour, which takes us much closer to a product that we could then put into a vehicle demonstration. Next slide, please. Now, when we're looking at vehicle demonstration, one of the things which is quite interesting is the potential as a sort of beachhead market to look at integrating onboard power generation into cool chain trailers. So in our fleet, we have some cool chain trailers like this on the front end of the trailers, on the bulkhead. There's already a small diesel engine coupled to a refrigeration system, and the potential is there. The form factor is really very suitable. The potential is there for us to swap out that fairly dirty diesel engine and put in an opposed free piston 2-cylinder engine that could generate 120 kilowatts of electrical power on demand using bioethanol, and then send that DC power to an electric tractor unit on those occasions when the tractor unit's onboard battery is depleted. So this is where we're looking ahead to a sort of concept of how the technology might first be used in a vehicle demonstration project. Next slide, please. This sort of module, though, has much wider applicability across a wide range of heavy-duty on-highway and off-highway vehicles. So although we might start putting this into a trailer-mounted range extender, obviously a tractor unit-mounted range extender has much broader use. And we can also look at the possibility of putting this into fixed wheelbase light and medium duty commercial vehicles, as well as off-highway applications like tractors, construction, forestry and mining. So that just gives you a fairly rapid run through of some of the areas that we see most interesting for alcohol fuels in heavy duty vehicles, and how Libertine's technology hopefully is going to provide the missing link between the excitement that I have and the prospects that I see for alcohol fuels in heavy-duty vehicles and the challenges that heavy-duty powertrains have today in moving to fully net zero capable future solutions. There we are. Thanks very much. I'll take questions later on at the appropriate time.
Thanks, Sam. Excellent. A quick run through there of the application of bioethanol. So we're now going to move on to a presentation from MAHLE Powertrain, and for that we're joined by Adrian Cooper. So Adrian has been Head of New Technology and Data Management at MAHLE Powertrain since 2017, but he's been at MAHLE since for the last 20 years. He's currently working within the Research and Advanced Engineering Group, where he's responsible for leading the research activities looking into powertrain electrification, advanced combustion systems and the use of alternative low-carbon fuels. So Adrian's going to share some of MAHLE's experience in the applications of some of these fuels. Okay then, Adrian, over to you.
Okay, thanks for the introduction, Steve. Yeah, in this presentation, I'd like to give a bit of an overview of our future hybrid powertrain concept that we came up with a few years ago, and go through some of the testing that we've done using some biogasolines provided by Coryton. So we have the next slide, please. So just a quick introduction to MAHLE Powertrain and who we are. We're a global engineering services provider specialising in the development of high efficiency powertrains. And we have sites around the world in Northampton in the UK, Detroit in the US, in Germany, and as well in Shanghai. The business originally came about from Cosworth, which was founded in 1958. And we were the road car division of Cosworth that were acquired by Audi in 1998. And then in 2005, we moved to ownership under MAHLE Powertrain. So we're a subsidiary of MAHLE, the component supplier, but we're also an independent engineering consultancy company who can work with MAHLE or independently from them. And we have a whole range of core capabilities that include engine design and development, transmissions and e-axles, electrification, controls and software development, as well as prototype assembly, testing and vehicle engineering and integration capabilities. Next slide, please. I'm sure a lot of you are very aware of this chart, and this is the trend in terms of fleet CO2 reduction amongst the vehicle fleets, and the sort of EU targets that are taking us towards the path towards net zero transport for 2050. So we have the EU targets of 95 grams for 2021, reducing to 59 grams in 2030. And that takes us on trajectory to pure electric by around 2045. And if we're going to achieve this, we need a really significant change in the vehicle fleet propulsion mix over the next decade. A new legislation's continually evolving and changing. So the UK gasoline and diesel ban proposal from 2030 and the EU Green Deal for 2030 to reduce the tailpipe CO2 emissions from 59 down to 43 to 48, all accelerating these trends. And these CO2 targets are obviously driving manufacturers towards increased electrification, whether that's through pure EVs or the use of plug-in hybrid electric vehicles. Next slide, please. So a couple of years ago, MAHLE started looking at what an optimum concept for a plug-in hybrid electric vehicle might be, and we developed our modular hybrid powertrain concept, which is a plug-in hybrid driveline that's optimized for the requirements of the next generation passenger vehicles. And it features an engine, traction motor, generator and transmission, and a dedicated hybrid engine, all fully integrated into one unit. Next slide, please. Oh, the colours come through a bit differently on here, but one of the key features of the modular hybrid powertrain is actually that the full dynamic performance of the vehicle is provided by the electric powertrain. So that differs from a lot of current plug-in hybrid solutions that are available on the market, which only offer a small proportion of the vehicle's performance using the electrical system. The system's combined with a plug-in solution and a battery pack, which gives us sort of 80 to 150 kilometres electric only range. So the vehicle can operate as a full EV over that limited range. We then have a dedicated hybrid engine, which is optimised specifically for the application. Because that engine is now only required to produce the charge sustaining power, the peak power and the peak torque of the engine and the operating range that it operates over can be significantly reduced. And that means we can optimise the engine for operating in that small window and boost the efficiency. It also means that the control of the engine is independent now from the driver demand, and that gives us the ability to much more accurately control the engine. We avoid sudden transient requirements, harsh accelerations of the engine and load shifts, and allows us to do improved emissions control. Due to the fact that we have the battery capability and we know we can predict when we need to start the engine, there's then opportunities to precondition the engine in terms of warming it by using waste heat from the electrical system, or preconditioning the after treatment prior to starting, all to help minimise the emissions. Next slide, please. So in terms of the layout of the modular powertrain, it's got 3 different modes of operation that we can run in. So it can run as a pure battery electric vehicle with the dedicated hybrid engine off and the transmission in neutral. Under low load conditions, we can run as a series hybrid, where the dedicated hybrid engine acts as a range extender and provides charge to the vehicle. But under high load and high speed conditions, we can also operate as a parallel hybrid, whereby the hybrid engine is providing direct drive to the wheels, and this is much more efficient under these situations than converting the mechanical engine energy from the engine into electrical energy, passing it through the battery system and back to the motor. The system's scalable, so we can configure it for a range of different configurations, from a compact car with a simple 2-cylinder engine and a 1-speed transmission, through to 2-cylinder engine for, say, a crossover vehicle, or a 3-cylinder engine combined with a 4-speed transmission for, say, a large SUV. So that provides the ability to give the normal towing capability, the long range capability that are expected of these kind of cars, without the need of a very large battery pack to provide that capability. Next slide, please. So when we started this study a couple of years ago, we wanted to look at what the optimum PHEV battery pack size would be. So we conducted some life cycle study. Obviously, life cycle studies are a very complex and rapidly evolving situation, and there's lots of different assumptions, and you can take values from lots of different reports, which can give you quite different answers. For this study, we were looking at the plug-in hybrid case and what was the optimum battery size, and we did the analysis based on a 1400 kilogram vehicle with a conventional engine that would produce 120 grams per kilometre of CO2. So it was typical in the market a couple of years ago. We've calculated the utility factors for the tailpipe weighted CO2 based on the R101 regulations, and we've considered well-to-tank contributions as well. We've used a grid CO2 intensity mix of 296, which was typical around the time of the study. And we also used a battery embedded CO2 value of 95 grams, which is taken from the recent Polestar study. But what this shows is, in terms of the sort of life cycle CO2, actually, which is depicted by this blue line, the minimum occurs where we have an EV range of around 80 to 150 kilometres from the system. And that means it's sufficient for most of the majority of journeys. It avoids the need to have a very large battery pack in order to achieve long journeys. But you have the backup of the modular powertrain in order to provide the high use capabilities, longer range, or towing capabilities and things like that. Next slide, please. So the dedicated hybrid engine that we've used is a 2 or 3 cylinder engine with a low technology pack featuring millicycle, high CR and external EGR. And because we've been able to reduce the operation of the engine, we can simplify it and reduce its complexity. Next slide, please. The engine features our MAHLE jet ignition system, which is a combustion technology which helps reduce burn durations and improve NOx capability, which enables us to run higher CRs and also have very high efficiency at a low cost. And with this engine technology, we're achieving over 40% brake thermal efficiency. Next slide, please. So now we get on to the biogasoline testing. The testing that we've done has been performed using the 3-cylinder modular powertrain development engine that we've described in the previous slides. And using that engine, we wanted to assess the impact of running different biogasoline blends on the engine performance. So we tested 5 Coryton fuels, which David introduced earlier. We tested 2 different 95 RON fuels, all compliant with EN 228, but covering a range of different properties that you could achieve. And we compared that against the 3 different biogasoline blends, which offer between an 80 and 65% greenhouse gas saving. Next slide.
2 minutes.
Okay, these fuels were assessed over a whole range of different operating conditions, covering all the normal operations. So from light load, whole map operation, full load, and a variety of typical conditions. Next slide, please. So we looked at the typical combustion metrics for the biogasolines, and we collated the data from all of those test points and looked at its effect on brake thermal efficiency, combustion duration, NOx resistance and combustion stability. If we have the next slide, please. And here we see an overlay of those same parameters for the biogasoline blends. And what we actually see is the good news is they perform in a very similar manner across all of the tests and all of the different fuels. We see a slight improvement in the high power thermal efficiency and improved combustion phasing with the higher RON biogasolines, as would be expected. And we also see a very small increase in the burn durations with biogasoline. Next slide, please. If we then look at the raw engine out emissions over the same suite of tests, looking at hydrocarbons, NOx, CO and PN flow, we see the results here for the conventional gasoline fuels. Next slide, please. And here's the overlay of the same results or the same tests, but with the biogasoline blends. And the emissions trends are overall very comparable. We see a slight increase in the total hydrocarbon and PN emissions with the biofuels due to the slightly higher proportion of heavy fractions within those fuels. But we also see a reduction in the NOx emissions. And it's expected that after treatment, when it's fully warm, these differences would actually be negligible. And we're planning further testing to look at alternative blends and to quantify the effect of these emission differences on tailpipe emissions in the future. Next slide, please. So if we go back to our sort of original charts that we look at and we see what effect the 80% reduction in tailpipe greenhouse gases based on the 95 RON biogasoline would make for a PHEV with an 18 kilowatt hour battery and 100 kilometre range. What we see is a reduction designated by the green dot, which takes us down, accounting for that greenhouse gas saving. If we then have a dedicated hybrid engine with full recuperation, we can generate low life cycle CO2 of around 80 grams per kilometre. And that translates to tailpipe CO2 emissions using the weighting factor in the region of 4 to 20 grams per kilometre, depending on the biogasoline content. For a product that's has the potential for use in sort of the 2025 type time frame as a new product, so it's well ahead of the sort of trajectory of the target for achieving zero tailpipe for 2050. Last slide, please. So in summary, the biogasolines that we've tested exhibit near identical combustion properties to the regular gasoline, and sustainable biogasoline offers the potential as a drop-in solution to help with CO2 reduction for the existing fleet with reduced life cycle CO2 contributions. And for heavy-duty applications, particularly, the plug-in hybridisation is an appropriate technology which offers a combination of local emissions-free driving, but long-range capability with only the requirement for a small battery. So a PHEV enables the optimised use of both battery and renewable fuel resources. And the MAHLE modular hybrid powertrain is an example of a future powertrain that could be scalable and cost optimised and provide high efficiency use of these fuels as we transition from current infrastructure to sort of a net zero transport approach. I think it's a complementary technology, and what we've hopefully shown with some of these testings is that the biogasolines, have the potential to offer comparable performance as a drop-in solution and can provide a contribution to reducing that overall fleet CO2 in the coming years. Thank you.
Excellent. Thanks, Adrian. It's really nice to see some real live test results of what some of these fuels can actually do. So thanks very, very much for sharing that with us. So it's going to move on to our final presentation now, which is going to come from Pat Symonds, whose career in motorsport has seen him achieve success with some of the sport's most accomplished teams and drivers, and has achieved achievements that are sort of too numerous to mention here and leaving time to do his presentation. So Pat is now Chief Technical Officer at F1, that's Formula One Management, tasked with setting up a small technical group to assist the FIA in the formulation of future F1 regulations, and we've seen a few announcements along those lines over recent weeks. So Pat's going to tell us about the opportunities that he sees for renewable gasoline in motorsport. So thanks, Pat.
Thank you, Steve. Well, this is an ambitious plan that we're going to talk about. I think it's achievable. And our aim is to reposition Formula One in the minds of fans, brands, and the naysayers that we do have to deal with as well. We hope it will enhance the relevance of the sport, and we hope it will also provide some commercial opportunities in the medium term. Next slide, please. So, sorry. I've lost it. Yeah, I can see it. So all the time we're doing this, we have to remember that really our mission statement is that we have to unleash the greatest racing spectacle on the planet. We mustn't lose sight of that. Next slide, please. So our programme covers all three pillars of sustainability: environmental, social and economic. And we're doing this to address front on the key challenges that Formula One is presented with today, for example, carbon emissions, diversity, etc. We want to proactively address these challenges that will come, and here we're looking at things like sustainable events. And we want to ensure that we have a robust response to the questions that are related to somewhat narrow thinking that we also have to deal with. But today, we're really just dealing with the on-track ambition. And next slide, please. So our target is for Formula One to be net zero carbon as a sport by 2030. And by that, we're covering the scope 1, 2 and 3 emissions, which are around 250,000 tonnes CO2 equivalent that we've measured. Next slide, please. So our carbon footprint analysis that we've already done was assessed across 2019, across the calendar year, 1st of January to 31st of December. And it showed just over 250,000 tonnes of CO2 equivalent for Formula One operations, team operations and Formula One races. It excludes the embodied carbon and it excludes carbon that's emitted by team suppliers. Now, if you include fan travel, where the figures are based on survey data, it does get to around 1.9 million CO2 equivalent tonnes. We believe that this is lower than FIFA World Cup 2018, Rio Olympics 2016, the Euro 2016 Championship, but the methodologies are different, so direct comparisons are difficult. But we continue to do competitor benchmarking analysis and trying to prove that Formula One can lead in this direction. Next slide, please. So before we look into the future, let's just have a quick look at the power units that we've used in Formula One over the last 25 years. At the top there, we've got the V10, great engine. Spectators loved it, but the efficiency was really pretty average. The V8 saw speeds that exceeded 20,000 RPM for a short while before they were reined back by regulation. And the power was pretty impressive for a 2.4 litre normally aspirated engine. It was the first Formula One engine that had a hybrid system, albeit a low power one, that was introduced during the life of this engine. And then we moved on in 2014 to the current turbocharged V6, which really brought a new philosophy to Formula One. So for many years, designers had been all about getting as much air as possible into the engine and then just adding the required fuel. And in 2014, we brought in a fuel flow limitation, which was around half of that used on the V10s at maximum power. And this brought a whole new philosophy of lean burn, as well as the much higher levels of hybridization. Next slide, please. Now, sustainability has been a bit of an untold story in Formula One's 70-year history, and it has now resulted in what we think is the world's most efficient hybrid engine. Many of the innovations that we've introduced have had a multiplier effect, improving efficiency across a wide range of industries. And Formula One technology has already significantly benefited road cars with aerodynamic innovations, safety developments, the energy recovery system itself, composite materials. Lots of things from Formula One have been adopted both by road cars and other industries. And we think that the hybrid engine combined with advanced sustainable fuels plays a role in decarbonising the global transport sector. The Formula One hybrid at the moment is the most efficient small engine on the planet. It delivers more power using less fuel than any car engine, and of course less fuel means less CO2. And we must remember that over 1 billion of the 1.1 billion vehicles in the world are powered by ICEs right now. So we think we can have a wider impact on more impact on the wider decarbonisation of the automotive industry through a sustainably fueled hybrid power unit. We believe that the solution to the environmental situation regarding mobility is going to be many parallel paths, not just one. Next slide, please. So as we consider our new regulations, we need to move to accept that energy is the new currency, not just of Formula One, but we think of society as a whole. We need to move to a formula that rewards energy efficiency even more than it does now, while keeping CO2 and other emissions extremely low. We need to embrace life cycle analysis, and we also need to help the public understand the implications of it, rather than what we think is a slightly illogical current focus just solely on exhaust gas emissions. And perhaps we'll move to an energy-based formula. At the moment, consumers pay for electricity in kilowatt hours, and they use gas with a conversion from cubic meters to kilowatt hours. So we wonder if we can get the same message across in motorsport. Next slide, please. We want to promote the technology. We don't want to be talking about sound. We want to be talking about efficiency. We want to talk about CO2 reduction. We want to call our cars plug-in hybrids, and we want to show that they are plug-in hybrids. Now, I think motorsport is very expert at moving technology through from a sort of TRL3 to around TRL8. We've done it many times before, and I think it's a core competence of our business. However, we've not always been very good at telling the world about it. And the veil of secrecy that surrounds competition has not been very helpful in this respect. But Formula One now is promoted by a media company rather than a venture capital company, so we have an opportunity to change this. Next slide, please. As we consider new regulations, we need to move to accept that energy is the new currency of everyone. And as I said, that means that we need to look at where we're going with our fuels. Now, our current regulations require that around 5.75% of our fuel comes from the bio source. We don't add to that at all, so there's no requirement that it's second generation, and there are no further stipulations. Formula One works on the fuel flow formula with a maximum flow rate of 100 kilograms an hour. And so the requirement really is to use this allowance to add the highest energy content. So consequently, everyone is using a synthetic isooctane, which is actually all coming from a single source, and it's doing very little to advance the science. Next slide, please. So for 2022, we're making a change. It's not a particularly challenging one, but we're going to remove the first generation isooctane and replace it with 10% of sustainable bioethanol. The fuel flow won't change, so we accept that there's going to be a slightly lower LHV of the blended fuel. And it's really a holding position until we move forward with a more challenging and relevant target. Next slide, please. The normal life of a Formula One engine is around 10 years, and the current engine was introduced in 2014. So we're looking really at introducing a new power unit for 2025. This allows many possibilities, and we need to be specifying an engine that will still be cutting edge as we approach 2040. Our thoughts are developing, but it does give us the opportunity to move to this energy-based formula. Now, currently in a race, we use 110 kilograms of fuel, and that fuel has an LHV of around 43 megajoules per kilogram. So we have around 4.73 gigajoules, or just over 1,300 kilowatt hours of energy available for the race. And maybe what we do is we provide regulations that drop this down to 900 kilowatt hours for the race, something like that. So we really promote the efficiency in that way. Similarly, with the maximum fuel flow rate, we can drop that down to perhaps 2/3, and we'll be adding power in with our electrical systems. So maybe our sort of 800 kilowatt target comes from 400 kilowatts from the ICE and 400 kilowatts from the electrical hybrid systems. And next slide, please. So I have to say that when we started with the 2014 engine, I didn't think we'd get to 50% thermal efficiency, but now we're targeting around 60%. Our brake-specific fuel consumption, we want well below 150 grams per kilowatt hour. And because synthetic fuels, which is where we're going, are expensive, I think reducing the use of them leads to a lower total cost of ownership, which can only be a good thing. Up to now, we've concentrated on fuel efficiency without too much concern of other factors. Now, particulates are not too bad on our engines because we have quite good combustion, but NOx is definitely the elephant in the room. And for 2025, we'll be considering that as well, with, for the first time, emission regulations coming into our regulations. Also, hybrids are heavy, and racing cars shouldn't be heavy. So we're looking at how we can reduce the power unit mass. We're considering a small, maybe 4-cylinder engine, for example, and thinking very carefully about how we size the battery. Next slide, please. So what might our next generation power unit look like? Well, the simple answer is I don't really know yet, but I do know that if we want introduction in 2025, we need to have a pretty good idea by the middle of this year. So we're doing a lot of modelling at the moment. We need to exploit the ability to use fuels with design characteristics that are pertinent to our specific needs, so a co-optimization process. There's no reason to only consider a single fuel source. I think octane on demand could be a useful technology, even though in our case the drivers might make a lot of demands. One of the success stories of the current engine is exhaust heat recovery at high loads. There's more that can be done here, and whether it's an extension of the current methodology, technologies such as the organic Rankine cycle. We need to consider much more hybrid integration, and I think Formula One needs to be a parallel hybrid for sporting reasons, but we do need to consider things like electric pit lanes, so we're showing the public that we have a true hybrid. The gas exchange needs further consideration. We've learned a lot from this engine, but there are certainly limitations that we need to overcome. Next slide, please. And one of the challenges we need to consider is that part of light load conditions are not of much interest to us. Now, I'm not saying that torque demand is binary. Drivability and smooth delivery of torque is vital, not just to vehicle handling, but also to tyre life and performance. So we need to consider how we integrate better our architectures, particularly with regard to integrating the electrical machines. I think time is not on our side for radical change to the internal combustion engine, but well-chosen cutting-edge technologies will serve us well. Some of the technologies are almost a given, such as HCCI and extremely high injection pressures, but the whole area of reduction of harmful engine emissions and after treatment is still very open to debate. Next slide, please. Now, moving to the sustainable fuels, we set a target to suppliers, relatively simple, relatively general, and we wanted them to produce some sample fuels that we could give to the engine manufacturers to test. And that fuel is now being produced and it's gone to the engine manufacturers. What we actually achieved, sorry, next slide, please. What we actually achieved was not far from what we asked for. The LHV was rather low and the performance was, of course, down a little bit, but it has at least shown that there is a starting point. Next slide, please. So now we're really looking at the pathways of where we can go in the future. And we have a matrix of opportunities, bearing in mind that we need to have somewhere around 750,000 litres of this fuel available in 2025 and sufficient quantities for extensive testing in 2024. I think that the e-MTG and e-gasoline have significant potential to be used as a base fuel, maybe around an 80% blend or something like that, but we would need further formulation to improve the RON. The e-Fischer-Trat naphtha can be upgraded as a stream or used for producing specifics such as cycloalkanes with desired sort of racing gasoline properties. But again, we need further process investigation on this. The format and the operating parameters of the 2025 power unit will ultimately dictate the optimum fuel, but I think the following considerations will be taken into account. Unfortunately, the LHV and the RON values are typically inversely related, and breaking this relationship is energetically quite expensive. So we'll probably put in a sensible RON limit of around 100, 102, and use advanced sustainable fuels that have a positive impact on the cost of the engine. And next slide, please.
2 minutes.
We have to consider the energy balance. I mean, this is one of the most optimistic that I've ever seen, and we can see that there's still a 3-to-1 ratio on this. But we are confident that the technology demonstrator is something worth doing and something that Formula One can certainly provide. The next slide, please. Just going to finish. Next slide, please. Thank you. Just going to finish off with a little movie that shows some of the work we've been doing. So next slide, please. Doesn't seem like it's coming through with any sound, which is a shame, but well, actually, without the sound, there's not quite much impact to it. So maybe we'll just move on to the next slide to finish off.
It's a shame. I could hear it.
So our mission now is not just to unleash the greatest racing spectacle on the planet, but the greatest sustainable racing spectacle on the planet. And as the video did point out, we've got to re-engineer racing. And the problem may have been pointed out by scientists, but only engineers, as ever, will find the solutions. And I think in Formula One, we not only need to be part of the solution, but we actually want to be part of it. So with that, I hope you've understood a little bit about what we're doing in Formula One for the future. Thank you.
Excellent. Thank you very much, Pat. Really informative and great to see everyone really taking the lead on this. So can I ask the other members, other presenters to join me now? Right, turn your videos and your microphones on, and we'll open the panel session. I think we can stop sharing, Gloria, then that would be great. Here we go. Excellent. 2, 3, 4. That's me. Excellent. I think that's everybody there. So thanks very much, everybody. Really interesting lineup of presentations. I think we had a really nice sort of introduction on to a range of the different fuels and applications, and it was good to see that range. One of the questions that came up in the chat was that, and I guess we'll start, Adrian, I'll start this with you, but I'll open it up to everybody, which is this all seems great, you know, sort of plug-in hybrid combined with some of these renewable fuels. Sounds like a really plausible solution. How much traction do you actually get with OEMs and customers when you're talking to them about, you know, modular powertrains, plug-ins and sustainable fuels, when there's just so much noise about the battery electric vehicles?
Yeah, I think that's a real challenge. I think these are sort of, you know, concepts that people are working on and looking into. But certainly the sort of pure EV range, it gets the sort of majority of the sort of focus, certainly within the sort of press at the moment. And I think, you know, it's a range of solutions that are appropriate, and developing that sort of range of different solutions, and maybe using, you know, biogasolines as drop-in solutions to help with sort of the transition period, offers some good ways forward. I think, you know, a lot of these things with, you know, some of the early technologies with sort of PHEVs, you know, one of the key things is actually making sure that people are plugging in and using the electrical capability of these systems as well. And it's how that kind of usage patterns are incentivized to make sure that we really are making the best difference with these different systems that are available.
Okay, does anybody else have anything to add to that?
I mean, I certainly can. I mean, from an OEM perspective, they're always going to be driven by policy. A lot of their, you know, what they decide to do is driven by policy. Thankfully, we are starting to see some, I'm going to say, some grown-up viewpoints coming out of German OEMs, really highlighting that there is still, you know, a viable solution available for the internal combustion engine. You know, it's got a future. You know, the key thing that we've been trying to educate a number of people is that the internal combustion engine itself it's good. It's not, that doesn't pollute. It's what you're fueling it with is what pollutes. And if we can change that, and we can prove that we can change that, then actually it's got some significant life on it. But it takes more incentive from the OEMs, from tier ones to support these initiatives going forward. You know, it is starting to happen. There's been a tremendous increase in wanting to sort of look into this now, and we just want to continue that drive. There's a lot of people here that, you know, some of my peers are on here as well, and they will see this. And you know, likewise with Pat and Formula One, you know, it's a good showcase to show that it's all viable, but we need more uptake.
Steve, if I just jump in there, just building on Adrian's point, I think the question of choice in terms of what the driver or the operator puts into the vehicle is really fundamental, and I think the second fundamental point is time is of the essence when it comes to the transition in vehicle technologies. I think in the case of heavy duty commercial vehicles, the resolution here is to get hybridization onto the road and to make sure that those hybrids are capable of using future renewable fuels, because then the choice of, you know, rolling around with battery power from the grid, which is likely to be the least cost source of energy, or rolling around with you know, fuels today from the forecourt and future fuels as they become more renewable, that choice can be driven by the economics as carbon pricing and mandates slide the cost of carbon up over time. But until we've got those vehicles rolling about, the choice is academic. I mean, until we actually have a significant penetration of battery electrification and plug-in electrification on the, you know, in the pool, in the sales, the choice is academic.
Yes, just building on that though, Sam, you know, it would seem, you know, if I was just listening to the presentations this morning, I'd be saying, well, hang on a minute. This sounds great. Why can't I just go and get some at the forecourt? It's a drop-in fuel. I don't have to change my car, and it makes a massive improvement. And yes, I might migrate, and I will be migrating to an electric vehicle over time, but I could start doing something about greenhouse gas emissions right now. Why can't I?
Absolutely agree. Personally, I'd like to see a fuel, a renewable fuel mandate being brought back in with much more ambition. We've got the means to increase the renewable content of fuel. We should put some policy ambition behind this. Yeah,
and there is some, through the renewable transport fuel obligation and things like that.
Like 6%. Yeah.
Yes, but they're quite hidden. Yeah, I don't think the public.
Where's the ambition?
But it's the awareness, isn't it? How do we build the awareness? And that's where I'm really excited about what F1 are doing, because this is a method of educating everybody, not only policymakers, but just waving a flag that there is some stuff we could be doing right now. Yeah, we don't have to wait and sit on our hands until 2030 or 2035. We could be doing some stuff now. So, Pat, what do you think? Is that something that you would really like F1 to be doing? Really, is being that showcase?
Absolutely, and I think we already are doing it. So as we sort of move towards thinking about what we wanted to do for 2025, we met with a lot of the OEMs at a very high level, at board level. And it's true that, of course, the focus is on electrification, battery electric vehicles, but equally they know that there are other things that need to be done. But it will be driven by policy, as someone said earlier. We've also met with the fuel companies just last week, again, at a similar, very high level. And we got very, very good support for sustainable fuels. So the background is there. So I think then, how do we change policy? How do we change perceptions? And I think these are the important things. Now, I'm very pleased to say that in mid-April, I think it's April the 13th, we've got a meeting, Formula One have a meeting with the government to discuss sustainable fuels. And this has come about because we're lucky enough to have one of our senior sort of PR guys actually used to work for Boris Johnson. So when he started talking about the things we were doing, Boris Johnson suddenly said, well, this is interesting, we ought to talk about it. So the process has started. And I think, again, as we generally talk to the public about these things, the perception will be there that actually there is something we can do. So, yeah, I really do believe we've got a role to play there. And while as an engineer, I like to look at the role we play technically, I have to say that I think right at the moment, it's the perception role is actually more important than the technical role right now.
Yeah, I think that was the point I was going to make. Is I think you mentioned actually in your presentation, Pat, that F1 does fantastic things and fails to tell anybody about them.
Yeah, we used to.
Yes. Okay. Well, under your guidance, then perhaps we can improve that situation. But one of the other things and criticisms often levelled, and I really struggle to get to the bottom of this, is we hear that there isn't enough of this stuff, be it biomass, biofuels, synthetic fuels, e-fuels, and that kind of stuff. So I'd be interested to hear on your thoughts on that. Do you think that's a valid reason for us not trying? Because that's what it feels like. It feels like, oh, there's not enough. Aviation's going to need it all, so we shouldn't bother. Just let aviation get on with that. Meant to be a bit of a provocative question. Who'd like to have a crack at that?
So I'll jump in there first, Steve. I think one of the things that I'm excited about the prospect of plug-in hybrid vehicles is you get two wins. Firstly, you can right size the battery. You can maybe do 80% of the miles, 90% of the miles using half the battery size than you would need if you had that remaining half of the battery for comfort reasons, right? So there's an immediate win in terms of battery materials, but also the quantity of fuel that you need to serve those edge cases where actually I just want to go a bit further than the 200 miles range on the truck or the car. that is best served by the renewable fuels, but you don't need very many of them because it's a very rare situation. So I think that plug-in hybrid architecture has a lot going for it, and it also, of course, gives policymakers and the driving public the choice in future of which they use based on price, and that can slide around.
Yeah. Okay. Absolutely. Thanks, Sam. Adrian, any comments on that?
I think I agree with the comments that Sam sort of said. I think it's really, I think, building up the use cases for these fuels and helping to, there needs to be a demand for them to help produce sufficient quantities. And if we're looking to use it in aviation in the future, we need to start building up that kind of supply capability as well. And we can use it in the sort of transition period.
Yeah.
I think just to add to that, obviously our usage is relatively small. Right now, Formula One uses around 1 million litres a year. That's going to come down due to certain restrictions we put in on dyno testing and things like that. But there are at least 2 reasonably large-scale plants that will come on stream in 2020. Well, actually, one of them in 2023, the other in 2024, one in Spain, one in Saudi Arabia, that will start to produce quantities that are way above what we need. Obviously, a drop in the ocean compared to global needs, but it is starting to get there. And as I said earlier, I think that the indications we got from the senior people in the oil industry were actually very, very encouraging, that they do feel that this is something that they need to get involved in. I think they realise, perhaps unlike, for example, the tobacco industry many years ago, who didn't accept that smoking was going to drop down, I think the oil companies have accepted that this is something that they need to get involved in if they want a business that's very similar to their core business to carry on.
Yeah. Okay. David, one question that came up earlier, and I know it's one I'm struggling with at the moment, is around the sort of various energy pathway efficiencies. We see lots of data on e-fuels, we see lots of data on conventional fuels, we see hydrogen or whatever, but actually getting pathway data on biofuels seems to be quite hard. What are you trying to do in this area?
Yeah, it's something that we've been trying to look into as well. And we are talking to a number of obviously the companies that we work with on these technologies. Is trying to understand, what is the energy going in versus what the energy is coming out of them. Unfortunately, because a lot of these processes they're still relatively new, they're all going through sort of these R&D phases or sort of pilots phases, and there isn't really a clear sort of guidance on what they are at the moment. Now we can make an assumption that versus say an MTG process, well, we know that something like the ETG process, it is significantly less, but it's not something we have full data on at the moment. But we are looking into it, and obviously when we look at these kind of figures, we need to be careful how we present them, because we need to be comparing like for like, i.e. we can't be comparing a demo facility versus what it will be like when it's up at full scale. So we've got to be mindful of those scenarios. So we're looking at the sort of the estimated values on that with the technology providers, and that's ongoing at the moment. And I'm sure at some point in the near future we will be publishing those as part of our efforts to continue to promote the fuels.
Yeah, I've seen certainly the JEC report that was reissued, what was it, end of last year, I think, that breaks all of these processes down from well to tank and tank to wheel and whatever. I've only ever managed to find the ethanol to gasoline, for example. I've managed to find the second generation ethanol, so you can get as far as the ethanol, but there isn't anything on the ethanol to gasoline, for example. So yeah, we need that data so we can. I'd love to produce that plot and just see how good this stuff is, because it feels pretty good, but that's not good enough, is it really? So, okay,
no, absolutely.
Yeah, thanks for that. Anybody else comment on those energy pathway efficiencies before I move on? Doesn't look like it. Sorry, phone's bloody ringing here. Sam, there was a question came up in the chat that I was intrigued by anyway. But with your power plant, you talked about, you know, one particular application on the refrigeration unit. What other applications could you see for that power, that sort of modular power plant?
So there are loads, and generally the applications that are of most interest, earliest interest, are those where it's hard for the grid to reach. Right, so that includes, I mean, I'm sat outside now, we've got the fields being ploughed, we've got some drainage work going on. All of that off-highway stuff is not going to go anywhere near a big kind of bit of charging infrastructure anytime in the next few decades. So off-highway as well as heavy-duty commercial, absolutely. Similarly, when we're looking at distributed power, you know, off-grid telco towers, for example, the nice thing about serious hybridization is the power generator is just responding to a sort of powertrain demand signal, right? It has no idea whether it's on wheels. So there's a great convergence opportunity between distributed power on the one hand and transport powertrain applications. And I think for that reason, we'll see a lot more of the tier one operators who historically have made, you know, systems and powertrain components for automotive, perhaps now being interested in the distributed power opportunity because they're essentially the same target market.
Yeah,
I just want to sort of add to that. I mean, you know, one of the things that we've been trying to promote here is to say, well, look at those captive markets. So, you know, I mean, the general public really not going to be that bothered. They're really not. They're far too cost conscious when it comes to that as well. But there are captive markets like the power generation markets, motorsport markets. Whether it's fleet operators for the supermarkets, they're the people that have got the image that they want to improve. They've also got the money, they won't want to admit it, but they've got the money to afford these types of fuels going forward and the technologies going forward. And they're a lot easier to supply into as well without having to look at the infrastructure elements.
Okay. There was another question that did pop up. I think it's a very quick question for you, David, that just said, do we have to, ethanol to gasoline, do we have to wait for the second generation lignocellulosic, or can we just use first gen if we have to?
No, so the simple answer to that is no, you don't have to wait. They are completely interchangeable with that respect. The only thing I would say is you're looking to utilise waste feedstocks for these fuels. The whole premise of fuels is that you don't want to compete for food crop. Sort of resource. Now that's slightly different in the US, where they've got an abundance of ethanol, and you know there are ethanol to gasoline technologies over in the US that are using first generation crop for that, because it doesn't really, as far as they're concerned, compete with food in that respect. But yeah, completely interchangeable. What we'll say is, can you put ethanol into a methanol to gasoline process and vice versa? No, you can't. The technologies are too different in terms of how they're splitting up the molecules. But yeah, first gen versus second gen, absolutely, completely
transparent. Yeah. Okay.
Steve, if I just jump in there with my ethanol hat on for a moment, I absolutely agree. Ethanol production should not compete with scarce food production, but what's scarce in food production are proteins and oils, not the starch. In the UK, I mean, we've got an abundance of starch crops. We're growing, you know, feed wheat outside now. It's barely worth growing. The prices are so low. They haven't moved in a decade. In the UK, we import protein crops from South America, and we are complicit in the deforestation that is driving. So the more first gen ethanol we produce in the UK, the less soy meal we import, right? There is no harm in that.
Yeah, absolutely. Oh, another question's come in, actually just building on what we were talking about earlier from Gainer here on. What challenges do you see for the infrastructure for these different fuels? Yeah, so we might want to think about drop-in fuels, but in Pat's presentation, he was thinking, looking ahead, could we actually start developing engines and fuels in tandem? Yeah, so that they're kind of co-optimized. And what might those challenges then be?
I'll pick up on that, Steve, because it's something we've discussed with the fuel manufacturers just last week, and they do say that, you know, having two streams available at the pump does cost an amount of money, but of course we do it now. You know, you can fill your car up with 95 or 98 octane, And there is no reason why you couldn't have what's now the 95 octane as a sustainable fuel, and what's now the 98 octane as a let's call it an advanced sustainable fuel for use in newer cars. You know, it's not quite that easy, because obviously, you know, there's the economies of scale and everything, and there is a cost to it, but it's certainly not impossible.
Yeah, just to add into that, there are a number of companies and whether it's the sort of engine companies or oil companies that have looked at technologies like gasoline compression ignition, octane on demand, as sort of Pat sort of shown in his presentation. So that the technology is there, it's been thought of, and the idea of this is, well, to look at, you know, some of the other feedstocks that could become available or are available now, but are not generally used because they can't, you know, they don't conform to your typical EN228, your EN590s, your STM specifications. It is something that's feasible, but again, it's the infrastructure. It can be changed, but again, you know, I'll go back to this. It's a bit of a mantra I keep on saying. For now, forget the public. You know, concentrate on the captive fleet scenarios. That's where you'll get the traction. Then roll it through.
Okay. Well, we're not right towards the end of our time. Does anybody have any final comments before I wrap up and hand back to Gloria?
I'd say just one. I did pick up on one question from David Spivey, who was asking about the energy in the process. Now, I'm not entirely sure if this was referring back to sort of the energy vectors, or whether it's the actual energy density of the fuel itself, but they are comparable with standard gasolines, i.e. fossil gasolines, in terms of the lower heating values on them. So they're all at around that sort of 42.5 megajoules per kilo, per kilogram.
Thank you. Andrew Fraser's just chipped in with an excellent one that we'll probably have to deal with offline, which is around what if we had excess ethanol and turned it, instead of going E10, turned it into the gasoline bit and then not worry about the blend wall. Yeah, that's another big conversation, Andrew. Right. Well, it just remains for me to just say thank you very much to David, to Sam, to Adrian, and then to Pat for sparing us the time and taking us through a very, very interesting set of presentations and a very stimulating panel discussion. All that remains now for me is to hand back to Gloria, who will wrap up and no doubt promote the remaining webinars in this series.
Yeah.
Over to you, Gloria.
Thank you so much, Steve, and thank you very much to our speakers, and thank you everyone for attending. Just to remind you all that we've got 3 more webinars. We've got Advanced Renewable Diesel this Thursday coming, Advanced Gaseous Fuels next Wednesday, and Sustainable Aviation Fuels next Thursday. So hopefully we'll see some of you there. So thanks again and goodbye.